Picture two walls standing side by side above a rising river. One was built last decade with laser-guided forms, engineered concrete mixes, and a crew of 200 specialists. The other was stacked by hand, block by ancient basalt block, by laborers in suspenders and flat caps, sometime around 1924. The river didn't care about credentials. When the floodwaters finally crested in the early hours of that October morning, something extraordinary happened. The brand-new wall, the one with the sensors, the computer models, the million-dollar engineering reports, gave way in a grinding roar of collapsing panels and churning gray foam. And the old one? Not a single crack. This is the story of a dam that history forgot, engineers dismissed, and nature refused to destroy. And buried inside its 100-year-old stones is a secret that modern construction has almost entirely lost. To understand this dam, you first have to understand the world that built it. It was the early 1920s. America was rebuilding after the First World War, and the country was hungry. Hungry for electricity, for irrigation, for control over the wild rivers that flooded farmland every spring without warning. Small towns across the rural West and Midwest were commissioning dams not because they had endless budgets, but because they had no choice. Engineering in that era was not about software models or tensile strength calculations fed into computers. It was about intuition accumulated over decades of watching what the land did. Foremen passed knowledge down not through manuals, but by standing next to a new hire at the quarry and saying, "Feel how this stone breaks. That split line is not your enemy. That split line is your joint." The men who built this particular dam were mostly immigrants, Slovenian, Italian, and Czech stonemasons who had been building with volcanic basalt in Europe for generations. They understood the material the way a carpenter understands grain in wood. And when they were handed a contract for a flood-control dam on a fast-moving river in the American West, they brought everything they knew with them across the Atlantic. They called it, simply, the stone wall. No grand name. No dedication ceremony. Just men with chisels and block and tackle rigging, raising one 600-pound stone at a time. Fast forward almost a century. The same river valley needed expansion. The old stone structure was deemed insufficient, quaint, even. A new flood barrier would be built alongside it using state-of-the-art reinforced concrete panel systems. The engineering firm's proposal ran to 400 pages. The structural models had been validated with finite element analysis. The concrete mix was computer-optimized for compressive strength, cure time, and temperature coefficient. Nobody consulted the old dam. The construction team was proud, and they had every reason to be, by every metric modern engineering uses. They were working with high-performance concrete rated at 8,000 pounds per square inch. They used vibrating compactors, laser-guided form systems, curing blankets with embedded temperature sensors. This was the best that 21st-century material science could offer. In their project debrief documents, obtained and reviewed for this story, one sentence stands out. Under the section on adjacent structures, a junior engineer noted, "Existing 1924 masonry structure has no engineering documentation. Structural capacity unknown. Not a factor in this project. Not a factor." That sentence would age very, very poorly. The atmospheric river arrived in late October, 3 years after the new barrier was completed. Meteorologists had tracked it for a week. 14 inches of rain in 48 hours. Not unprecedented for the region, but rare. Emergency managers activated flood protocols. Sandbag crews were deployed. The new barrier's sensors went online, transmitting real-time pressure readings to a dashboard in a county emergency operations center 30 miles away. By 2 a.m., the river was already 6 feet above flood stage and climbing fast. By 3:15 a.m., the pressure sensors on the modern barrier were sending alerts. At 3:47 a.m., a concrete panel joint began to fail, a hairline fracture that widened in under 4 minutes as the hydraulic pressure found the path of least resistance. Within 20 minutes, 3 adjacent panels had separated from their anchor bolts. Water was pushing through the gaps in white, roaring sheets. By 4:30 a.m., a 140-foot section of the new barrier had collapsed. And through all of it, through every shuddering impact of debris, through every wave that crested and rolled and pounded, the old stone dam held. Eyewitnesses in the county emergency report described watching chunks of the collapsed modern barrier slam against the basalt stones at high velocity. The stones did not move. Not one joint opened. The structure absorbed the impact and stood. When dawn broke, the engineers and emergency managers surveyed what remained. On the north side of the river, a 140-foot gap where the modern barrier had been, filled with tangled rebar, crushed concrete panels, and debris from upstream. Fence posts, roof sections, a ruined grain trailer. The structural failure had allowed a surge of water that caused an estimated $40 million in downstream damage. On the south side, the 1924 stone dam, completely intact. A structural engineer named Dr. Petra Okafor, brought in by the county for the post-event assessment, walked the length of the old structure that morning. She later described the experience in a paper published in the Journal of Structural Engineering. I was looking for the failure point. I walked it twice. There wasn't one. The structure had experienced impact loading from debris at velocities I would not have predicted it could survive. And it had survived them, apparently without effort. Without effort. She took over 300 photographs that morning. She chipped mortar samples. She measured joint tolerances with calipers. And as she worked, a question began forming that would consume the next 2 years of her professional life. Why? Why did this thing survive? Dr. Okafor's investigation ultimately identified 4 interlocking reasons why the 1924 dam survived, and none of them were accidents. The first was the material itself. Basalt, the volcanic stone used throughout this structure, has a tensile and compressive strength profile that changes under load in a fundamentally different way from concrete. Where concrete is rigid and transfers stress along predictable shear planes, basalt is slightly elastic at the microscopic level. Under impact loading from debris or water pressure, the individual stones flex microscopically, distribute the force across dozens of contact points, and then return to position. Modern engineers have a term for this: ductile behavior. The old stonemasons didn't have the term, but they knew the behavior because they'd watched it across generations of work. The second was the mortar. Lab analysis of samples taken from the dam revealed a lime-pozzolan mix, a formula with roots going back to ancient Rome. Specifically, the Italian stonemasons on this crew used a natural volcanic ash they called puzzolana, sourced from deposits in the same region as the basalt. This mortar, unlike modern Portland cement, continues to strengthen with age. After 100 years, the mortar joints in this dam are actually harder and more cohesive than they were when they were laid. Modern concrete weakens over decades. This mortar grew stronger. The third secret was the joint pattern. Modern concrete walls carry load through shear between vertical panels, a fundamentally vulnerable geometry when hydraulic force is applied perpendicular to the face. The stonemasons used an interlocking pattern called opus incertum, irregular stone placement that means no joint ever aligns vertically with a joint above or below it. There is no continuous fracture plane. Force arriving at any point on the structure must travel through stone before it reaches a joint, and when it reaches that joint it must change direction before it can continue. The wall doesn't just resist force. It confuses it. The fourth factor is the one that most surprised Dr. Okafor. Looking at original construction photographs, discovered in a county archive, she noticed that the builders had intentionally incorporated a slight downstream lean into the structure. Not much, approximately 2 degrees off vertical. Modern engineering standards would flag this as a construction error, but it isn't an error. A wall with a slight lean into the direction of expected force is geometrically preloaded to resist that force. The river pushes, and the structure's own weight pushes back harder. The lean is not a flaw. It is the solution. Dr. Okafor's paper landed quietly in the academic world, but its implications were anything but quiet. Because the 4 principles she had identified in this dam aren't obscure historical curiosities. They are principles that were standard in masonry construction for over 2,000 years, from Roman aqueducts to medieval cathedrals to 19th-century railroad bridges. And they didn't disappear because they were superseded by something better. They disappeared because they were superseded by something faster and cheaper to produce at scale. Portland cement concrete, the material that now dominates global construction, was patented in 1824 and mass-adopted through the 20th century because of 2 things: speed and standardization. A concrete wall can be poured and formed in days. You don't need a highly skilled mason with 20 years of experience in volcanic stone. You need a foreman, a mixer truck, and a blueprint. That efficiency came with a trade-off nobody fully accounted for at the time. Concrete structures, even well-built ones, are designed with a service life in mind, typically 50 to 100 years. After that, the carbonation of the concrete matrix weakens it, the rebar begins to corrode, and the structure needs to be replaced or heavily retrofitted. It's not a failure of the system. It's the system working exactly as designed. But when you build a flood barrier with a planned obsolescence, and then a flood arrives that your replacement schedule didn't account for, the consequences are downstream, in every sense. Meanwhile, the basalt dams, the limestone bridges, the granite retaining walls built by skilled immigrant masons 100 years ago, many of them are still standing. Not because they were built for the ages by men with loftier ambitions, but because the materials and methods they used happened to improve over time rather than degrade. We didn't lose this knowledge because it was wrong. We lost it because it was slow. The story doesn't end in failure. In the years since Dr. Okafor's paper was published, it has been downloaded over 90,000 times and cited in 43 subsequent studies. It has been referenced in infrastructure planning documents for the European Union, for the U.S. Army Corps of Engineers, and for coastal protection projects in Bangladesh and Indonesia. A small but growing movement in structural engineering is now looking backward, not as nostalgia, but as research. Teams at universities in Italy, Japan, and the United States are reformulating pozzolanic mortars using modern quality control standards. Researchers in Scotland have been studying the interlocking geometry of traditional drystone walls to apply similar load distribution logic to seawalls facing increased storm surge from climate change. And that forgotten 1924 dam? It has been officially listed on the National Register of Historic Places, not as a relic, but as a research site. Engineers come to study it. Architecture students sketch it. And it continues to do its job, quietly and without complaint, as the river that couldn't break it rolls past its ancient stones. There is a tendency, in our era of computational design and advanced materials, to assume that the most recent solution is the best solution. The history of the stone wall suggests something more complicated, that certain problems were solved, in some essential way, a very long time ago, and that the solution was not discarded because it failed, but because it was replaced by something that could be produced faster and at a lower upfront cost. The question now being asked in structural engineering circles, quietly, carefully, but with growing urgency, is whether the accounting was right. Whether the full cost of our materials, spread over the true lifespan of our infrastructure, was ever really calculated. The 1924 dam knows the answer. It has known it for 100 years. It's still waiting for us to come and listen.